So hello everyone and welcome back to a brand new video, and in this video I'll be solving problem C, that is number game, from add round 138, and I will also make a video on problem D, so stay tuned for that as well. Also, one more important thing, I recently posted on LinkedIn about my internship offer, so I will drop a link to the post down below, so please go on the post and show some love so I can get some engagement and some reach. Yeah, so that was it, and let's move on with the solution now. Before we move on to the solution, I want to take a small break and tell you guys about Newton School's premier coding contest. So as all of you guys love CP and all of you guys love to code, this is a great opportunity to show off your coding skills and also win some cash prizes. There are prizes worth rupees 30,000, and along with this you can also win some free coding courses or also grab some internship opportunities. Right, so for this reason only, Newton School organizes this contest every month on a global scale, so you can also benchmark yourself where you are lacking or where you are standing compared to other students. So this month it will be on 27th October. It will be around 2.5 hours starting from 9 p.m. and it is absolutely free to sign up for. So there will be a link down below, so do check out that link and sign up for the contest for absolutely free. Yeah, so let's move on to the solution now. So in the problem, we have been given an array of size n where n is up to 100. So something like a1, a2, a3, so on up to an, right? Where all the elements ai are from 1 to n. So there are no negative elements, all the elements are positive and they are lying from 1 to n. Secondly, we have two people, Alice and Bob. Both of them are playing a game with k rounds, right? And in every round both of them will play a move. So let's say we are at some ith round out of the k rounds. So Alice will move first and she will choose some element, let's say ax, such that ax is less than equal to k minus I plus 1, and she will remove the element ax, right? After this, Bob will move. He will choose some element ay and add k minus I plus 1 to element ay, right? So he will set ay is equal to ay plus k minus I plus 1. So these are the two moves. We say that Alice wins. We say Alice wins if she can move for all the k rounds. If she can move for all k rounds. That is, if Alice can find an element to remove for all the k rounds, then we say that Alice wins. And if for some round Alice is not able to move, we say that Alice loses. And if Alice cannot move, for some round I less than equal to k, we say that Alice loses. So that is the game. So given this, you have to find the maximum value of k such that Alice wins. So given this, we have to find the maximum value of k such that Alice wins. And that is the problem. So given a game with two people, find the maximum value of k such that Alice wins. So how can we solve this? Let's move on to the observations. So the first observation, that is, Bob will never apply more than one operation on the same element. How can we say this? We can do a simulation. Let's say we have a first round. Value of k minus I plus 1 in this round is how much? This, as value of I is 1 here. So k minus I plus 1 is k minus 1 plus 1. So this is equal to k itself. So first Alice will move. She will take some element ax which is less than equal to k and remove ax. Second, Bob will play the move. He will take some element ay and add k to that element, right? So we will do ay is equal to ay plus k. Then we move on to the second round. The value of k minus I plus 1 is how much? This is equal to k minus 1. So now Alice will choose some element ax which is less than equal to k minus 1. But the question is, will she ever be able to remove ay? Right? Will she ever be able to remove ay? The answer is no. The answer is no. Why so? Because now value of ay is equal to ay plus k, right? And ay plus k is obviously more than k minus 1, right? And Alice can only remove elements that are less than equal to k minus 1. So she will never be able to remove ay, right? So basically you can say that Bob has locked element ay, or you can say he has fail proofed element ay. So in one operation, Bob is able to lock an element, and in the future Alice will never be able to remove locked elements, right? So if you apply just one operation, you can lock an element. So that's why using two operations on an element is not useful, right? Because if you are able to lock an element in just one operation, why do you need to apply two operations on that, right? So you will always use just one operation on element, and using that one operation you will lock that element, and that element will never be removed in the future. So that is the very first observation. Now let's move on to the second one. So the second observation is the constraints. So if you look at the constraints here, number of test cases are up to 100, n is also up to 100. So we know that number of test cases t is up to 100, n is also up to 100, and the number of rounds, in every round Alice will remove an element, right? So the maximum number of rounds that we can have are equal to n. So k can also only be equal to n, so that is equal to 100 also. So if you see the constraints, you can say that t into k into n is equal to how much? This is equal to 100 into 100 into 100, that is equal to 10 to the power 6, right? So that gives us a hint that we can, for all the test cases, we can iterate for all the possible values of k, right? We can iterate for all the possible number of rounds, and for every round, for every value of k, we can simulate over the array, or we can iterate over the array of size n, right? As t into k into n is less than equal to 10 to the power 6, so we can easily make these iterations. So for every test case, we will iterate for every value of k, and for every value of k, we will just simulate the game over all the elements in the array, right? So that will be our approach. So the constraints help us to see an approach. The approach is simulate the game for all values of k and choose maximum k value where Alice wins. So that will be our approach. So we will, for every test case, iterate over all values of k, and for every value of k, we will simulate the game, and then we will choose the maximum value of k where Alice wins. Another doubt that you guys might have here is, what if value of n was large? If value of n was large, we could have used binary search. But here the constraints are small enough that we can do a normal simulation. So we will be doing simulation instead. So that's why we will not go for binary search. We will use simulation because the constraints are small enough. If constraints were large, we could have gone for binary search, right? So now we need to do the simulation. So we need to simulate the game. So if we need to simulate the game, we need to find the optimal game theory, right? Because if you have to simulate a game, you need to know the optimal moves that both of them will play. So basically you need to find the optimal game theory for both the players. Then only you can simulate the game, right? So now the next step is to find the optimal game theory for both the players. So now let's try to do that. So the next step is optimal theory for both the players. So let's first try to find the optimal theory for Alice. So the optimal game theory for Alice. In the first round, Alice can remove elements that are less than equal to k. In the second round, she can remove elements that are less than equal to k minus 1, and so on. In the kth round, she can remove elements that are less than equal to 1. So what do you guys feel like will be the optimal strategy here? Is it optimal if I decide to remove smaller elements in the first round, right? Let's say I decide to remove a 1 in the first round. Is it optimal or not? Obviously it is not optimal, right? Because in the first round I have many choices. I can either remove 1, 2, 3, so on up to k. But in the last rounds, in the kth round, I only have one choice. I can only remove a 1, right? So if I decide to remove a 1 or some small element in the first round, I might need that element in the later round, right? It might happen that if I decide to remove a 1 here, I might need that 1 later in the last round. So it is never optimal to remove smaller elements because I might need those elements in the later rounds, right? So we get a hint that it's not optimal to remove small elements, as we might need them later, right? So the optimal strategy will be to find the largest element. So in the first round, we will find the largest element that is less than equal to k and remove that element, right? So the optimal strategy for Alice, optimal strategy will be for Alice to find largest element less than equal to k minus I plus 1 in ith round and remove that, right? As we need small elements for later, find the largest element that is less than equal to k minus I plus 1 and remove that element in the ith round. So that will be the strategy for Alice. So now let's see how we can find the strategy for Bob. Optimal strategy for Bob, right? One of the strategies that you guys can think about is in the first round, Alice will remove a element that is less than equal to k. So she will find the largest element that is less than equal to k and remove that, right? And in the second round, she will find the largest element that is less than equal to k minus 1 and remove that. So one of the strategies that you guys can think about is we can find the element that Alice will remove in the next round and lock that element, right? Let's say she is going to remove some element ax in the next round. So we can find that element ax and lock that element. One of the possible strategies is this. But will it help? So let's try to draw an example and let's see if it will help us. So let's say my value of k is equal to 3 and my array is something like 1, 1, 2, 2 and 3, 3. So Alice, so in first round, Alice will move first and she will remove the largest element that is less than equal to 3. So she will obviously remove this element. Now in second round, she will remove element that is less than equal to 2. So she will remove one of the 2's, right? So she will remove one of the 2's. So Bob, seeing this, will lock one of the 2's. So he will lock this element because we know she is going to remove a 2. So we will find one of the 2's and we will lock that 2. So we will lock this one. So now Alice has to remove an element that is less than equal to 2. Bob has locked one of the 2's, but we have the second 2. So now Alice will remove that 2. So now Alice will remove this one. Now seeing this, now in the third round, Alice will remove an element that is less than equal to 1. So seeing this, now Bob will lock the element that is 1, right? So now Bob will try to lock 1. As we know, Alice is going to remove 1 in the next round. So we will try to lock this 1. But in the third round, now Alice has to remove element that is less than equal to 1. Bob has locked one of the ones, but we have a second one. So Alice will just remove that and she will win 3 rounds. So now you can say that Alice wins in 3 rounds. But the strategy that Bob used here was not optimal, right? Because let's try to draw the example again. 1, 1, 2, 2, 3, 3. Alice removed 3. The optimal strategy for Bob should have been to remove the smaller elements, right? Because if you see in the last round, Alice has very few choices, right? So instead of sabotaging the higher rounds, Bob should try to sabotage the lower rounds because the choice in lower rounds is very less. So Bob has more chances to sabotage the last few rounds instead of the first few rounds, right? So strategy for Bob, instead of sabotaging next round, try to think long term, right? Try to think long term and sabotage last rounds. That is, if you want to sabotage last rounds, the optimal thing for that is remove smallest elements. So if we try to apply that strategy here, Alice removes 3, we will remove the smallest element, that is 1. Now Alice will remove 2. Now Bob will again remove 1. Now in third round, Alice has to remove an element that is less than equal to 1, but there is no element left that is less than equal to 1, right? So Bob wins here. So our strategy works. So the optimal strategy is to sabotage the last rounds. That is, to do that, we have to remove the smallest elements. And now we know the optimal strategies for both the persons, for Alice and for Bob. So now we can simulate the game process. So now let's do that. How can we simulate it? So you can say approach, or you can say simulation. So we can just sort the array A1, A2, A3, A4, so on up to AN. Just sort the array, right? Sort it. First of all, Bob will remove the smallest element. So Bob, pointer of Bob will be here, or you can say Bob will be on the left side. Let's say Bob is on the left side. First Alice will move, so she will first find the element that is less than equal to k. So let's say the element is here. Let's say it is some element AX. So she will first remove this element. Now Bob will move. So Bob will now remove A1, or lock A1, you can say. Now Bob will lock A1. So Bob moves here. Then Alice will again try to find an element that is less than equal to k minus 1. So let's say she finds some element AX dash. So now she will remove AX dash. Now Bob will also remove the smallest element again. So he will now move to A2. Now he will lock A2 and he will move here. So on you can keep on simulating. If you are able to like do k simulations, or you are able to do k rounds, then Alice wins. Otherwise Bob wins. And using this, for every k value you can simulate and find if that k value, in that k value Alice wins or Alice loses. So for every k value, do this simulation and check if Alice wins. This is basically a 2-pointer, right? Bob is on the 0th side and Alice will start iterating from right, and whenever 2 pointers meet, check if Alice is winning or not. So that is the entire process. And if you guys want to see the code for this, here's the code. So we will take our array V, we'll sort the array. Then we'll start from value of k that is equal to n while k is greater than 0. And we'll start iterating over all values of k. Then I will keep my pointer. Pointer is n minus 1. This is for Alice, and round is equal to 0. This is for Bob. So number of Bob moves will be equal to number of rounds, right? So Bob moves so far is equal to number of rounds. That is 0 in the starting. So while round is less than k and pointer is greater than equal to Bob moves so far, so I will keep iterating towards the left until I have reached the locked element, right? So I will keep iterating, and if I am able to find an element that is less than equal to k minus I plus 1, I will say rounds plus plus, and I will say Alice have found the element, and I will break out of the loop and I will increase the number of rounds. So I will simulate for k rounds, and if in the end number of rounds are equal to k, I will just print out the value of k, that is I have found my answer. If the number of rounds are not equal to k, that is I was not able to, the Alice was not able to win, right? So in that case, I will decrease my value of k and then do the same thing for that k value. So that is the entire solution. Rest is just implementation, right? I don't think the problem was that hard. The problem was just implementation. So if you guys have some doubts, feel free to join my Discord server again, right? Feel free to ask your doubts there. I will be more than happy to answer your doubts. And don't forget to like my LinkedIn post. So do check out my LinkedIn and like this post. It will help me a lot. And that was it for this video, and I will see you guys in the next one. Bye bye.